Let's now come back to an idea that we discussed earlier in the context of Anscombe's quartet and the data source dozen, namely that one-dimensional statistical summaries often fail to capture the full picture. This slide takes that abstract idea and applies it directly to a logistics use case. Checking the plausibility of data, in this case, item master data such as product length, width and height. What you see here is a box plot visualization of three variables: product length, product width and product height. These are item dimensions taken from a master dataset. Before we dive into the mechanics of the box plot, let's clarify what we mean by plausibility. In this context, we're not checking whether the data is correct. We're checking whether it makes sense, whether it fits into what we would reasonably expect, given the physical world and the operational context. A product with a length of 60 centimeters, a width of 40 centimeters, and a height of 30 centimeters. Sure, plausible, that's a typical carton. But what if we have a product that supposedly has a width of 0 or a height of 1,500 millimeters when most other products are 100 or 200, or a length of 999 centimeters, which would be almost 10 meters? These values may not be wrong in the technical sense, but they are likely outliers, entry errors, or at least items requiring special treatment. And here's the key point. Detecting those implausible values is crucial before we feed the data into layout planning, automation models, or even basic throughput simulations. Now, remember Anscombe's quartet. All four datasets had the same mean, the same variance, the same regression line. And yet, visually, they were completely different. The same logic applies here. Let's suppose we only looked at the mean and standard deviation of product length. What would we see? A mean of, say, 150 millimeters, a standard deviation of 60 millimeters. Nothing particularly unusual, right? You might think, okay, most products are between 90 and 210 millimeters in length. Sounds good. But that conclusion would be misleading. Why? Because the outliers get buried. They get absorbed into the summary numbers unless they are extreme enough to pull the average. But even then, averages are notorious for their inability to signal anomalies. They smooth out the data. They hide surprises. This is where box plots come in. A box plot is a type of statistical chart that's designed specifically to highlight outliers. Let's break down what you see in a box plot. The box shows the interquartile range, that is, the range within which the middle 50% of your data lies. The line inside the box is the median, the 50th percentile. The whiskers typically extend to 1.5 times the interquartile range. And the dots beyond the whiskers? Those are outliers, data points that lie far outside the typical spread of the data. If you look at the leftmost box plot for product length, you'll notice a dense cluster of outliers above 250 millimeters, some even pushing up toward 2000 millimeters. That's 2 meters, well beyond what you'd expect for normal cartons. Now, does that mean these items are wrong? Not necessarily, but they deserve a second look. They might be oversized products that need special storage locations, misinterpreted dimensions, e.g. someone typed 1200 instead of 120, placeholder values or defaults from legacy systems. The point is, you wouldn't see it from the mean and standard deviation alone. And in a histogram, which is another type of graphical representation we could use, these outliers might be difficult to detect too. In the box plot, however, they can be identified at first glance. So how does this relate to logistics? Why are we spending time talking about box plots and plausibility? Because every warehouse design project, every automation implementation starts with data. If your master data contains implausible records, say items that are too big to fit in the bins, or with weights that contradict packaging types, your entire design will be flawed. You'll misestimate required storage space, overload shelving unintentionally, undersize totes or bin compartments, break cartonization logic in automated systems, or design pick routes that are unfeasible in practice. Here are a few hands-on tips for applying box plots in your data analysis work. Always plot dimensions separately. Length, width, and height each deserve their own plot. Investigate outliers interactively. Once outliers are identified, pull the original records. See what product they refer to. Ask, does this make sense? Don't delete outliers blindly. Some of them are real. Instead, tag them, comment them, and decide how they'll be treated in downstream processes. Use visuals early. In workshops with clients, show these plots. They often help non-technical stakeholders understand why their own data needs cleaning. To close this part of the lecture, let me repeat one core insight. Data analysis is not about numbers. It's about meaning. And meaning comes from interpretation, not aggregation. A good analyst doesn't just summarize. A good analyst explores, visualizes, and questions. This, by the way, is one reason why I think that every logistics engineer should have a very good understanding of data analysis. If you simply outsource the data analysis to the data analysis department, then you lack the insights that would allow you to ask good questions and possibly detect mistakes. At the same time, the data analysis may not have the deep understanding of logistics engineering that is needed to extract the right information from the data.